So any queries for anybody or the previous session? What we discussed so far? To anyone? Then the objective of today's session will be on normals drawn to conicoid as well as ellipsoid. So we discuss the concepts with regard to this topic in today's session. So from Thursday onwards, we are going to start a new topic, that is abstract algebra or modern algebra, whatever you say. So tomorrow we will finish majority of the portion, and in next day class also, if you have any doubts, I will take a doubt clarifying session separately, and I will give the supplementary material for you for your reading and consideration as per your interest is concerned with regard to this conicoid topic. And I am preparing the assignments for you randomly. So once you finish with the solid geometry, you can go through the assignments, ask your doubts in the meantime, right? That is my idea with regard to the class sessions. So may I know, are you following any textbooks with regard to the solid geometry or analytical geometry so far? Or you are just taking the video lessons right now, then you are going to prepare yourself as per the free time. Okay, go ahead. Then let us begin our today's session. Suppose you consider the surface, say it may be a conicoid or ellipsoid, whatever the case may be. If we have taken a point on it, at this point you are considering a normal to it, the perpendicular line to this surface. And with regard to the problems of this model, we require a small visualization. Initially it takes a little time for you for the visualization part. Slowly you will get adjusted to the situation, right? So I am going to write the respective formula for it. You please take a note of those things. So give me a moment, I am going to write that. Suppose you have taken the conicoid ax square plus by square plus cz square equal to 1, and at the point alpha, beta, gamma, I want to consider a normal to it, and equation of the normal is given by so this is the formula we use, which is the equation to the normal. Actually, there are two formulas while writing normal equation to a conicoid. So occasionally we are going to solve problems based on the distance criteria. So in that particular case, we will write the equation of the normal using the actual direction cosines of the line. Apart from that, for general problems, we consider the normal equation of the line where drs are there in the denominator. Okay, you please take a note of that. And the other equation, you can call it as So here P is the distance considered from center of the conicoid to the tangent plane. So this equation of the normal generally we consider while solving the problems based on the distance. This is the normal equation we consider for the other problems. And the value of the P is given by this formula, which is already known to you. So for the conicoid, the formula for the normal equation is this, the normal line equation. You take a note of that. If you have taken the case of ellipsoid, you can say the equation of the normal to the ellipsoid is given by you take a note of that. And if you want to use the actual DCs, it is given by this equation we consider. And for that P, we have a standard formula. You take a note of these values. For conicoid, this is the normal equation we use. This is also the other formula. For ellipsoid, this is the normal equation and this is the other formula for normal equation where P measures the distance. So let us take the first problem. The normal at P alpha beta gamma of a central conicoid meets the three principal planes at G1, G2, G3. Show that please take a note of the problem. Then we discuss with the approach. So in this problem perspective, with regard to this part, so we need to understand the problem statement very carefully, and while evaluating the answer, we should be cautious in taking the exact normal equation. Right. So let us start with the approach. See, I have considered the conicoid. Say, this is the center of the conicoid. By default, the center is nothing but origin. So, let us imagine that this is x-axis y-axis and z-axis. So I have taken a point P alpha, beta, gamma on the conicoid. And it is saying that if you consider a normal at P, it is intersecting the three principal planes. So it is intersecting xy plane, yz plane, zx plane. The principal planes are nothing but the coordinate planes at the points g1, g2, g3. So what happens if you consider the distance pz1, similarly they consider pz2 and another one pz3, the distances values, they are in a constant ratio. That we have to prove actually. So don't misunderstand that I have taken a normal from P to the axis directly. Don't misunderstand. You imagine the space, you imagine a surface there. On the surface, if I draw a perpendicular line, it is meeting the planes. You imagine like that. Because the difficult part here is imagination. It is not possible to draw the picture on board. However, you understand that if I have chosen one fixed point P, the normal drawn to the surface is meeting the three coordinate planes in the points G1, G2, G3. That you need to understand here. Is it clear now? Say. Right. Now, at the first place, I want to write the conicoid equation, which is nothing but ax square plus by square plus cz square equal to 1. Please understand, I am considering the distances here. So, I am writing the normal equation, which is given by x minus alpha by a alpha p, y minus beta by b beta p, and z minus gamma by c gamma p. This is the equation of the normal at this point P. And we have a specific value for P. It is nothing but P is equal to 1 by square root of a square alpha square plus b square beta square plus c square gamma square. This is the value of P there. And you take the ratio constant R here. You have written the normal line equation in the symmetric form, and this is the parametric constant R. Okay? Are you clear up to this part? Now, it is meeting the principal planes, right? So, if you consider the principal planes, the equations are nothing but x equal to 0, y equal to 0, z is equal to 0. First plane, second plane, and third plane. Now, you are involving the actual direction cosines here in writing the normal equation. So, here R is nothing but the distance, the actual distance, because you have written the line equation using the direction cosines. So what happens, if I substitute x equal to 0, the distance R is nothing but Pz1. As per the problem, it is Pz1. You get the point. So substituting x equal to 0 here, we will have 0 minus alpha by a alpha is equal to Pz1. So this gives that Pz1 is equal to minus 1 by AP. Please check that. Similarly, If you substitute y is equal to 0 and z equal to 0, the respective values are nothing but Pg2 equal to minus 1 by Bp, Pg3 is equal to minus 1 by Cp. I have substituted y is equal to 0. From this, you got the Pg2 value. I have substituted z equal to 0. I got the value of Pg3. Okay? We accept or not? Now, if you read the question problem, we have to prove that the distances Pz1, Pz2 and Pz3 are in a constant ratio. What does it mean? If you calculate the ratio for the distances, it should be a constant. So, if you consider the ratio for Pz1 is to Pz2 is to Pz3, it is nothing but minus 1 by AP is to minus 1 by BP is to minus 1 by CP. So cancelling the negative symbol and P itself, it is nothing but 1 by A is to 1 by B is to 1 by C. So the distances are in a constant ratio. Okay? Why? Because ABC are nothing but the constant values in the conicoid. So since ABC are constants, the ratio is a constant here. Clear for everyone? The first part of the problem. Please take a note of that. The actual DCs are nothing but A alpha P, B beta P, C gamma P. Principal planes are nothing but the coordinate planes, XY plane, YZ plane, ZX planes. So if you consider YZ plane, the equation is nothing but x equal to 0. If you consider ZX plane, the equation is nothing but y equal to 0, like that. So just imagine a situation that, so if you have taken the ellipsoid, the center is nothing but origin. So you fix the 3 coordinate axes, around that you have a surface. So the coordinate planes are nothing but the principal planes. Clear? Right. Any questions with regard to the first part of the problem? Please understand. If you involved the DCs here, actually let me say, I will give one simple example. Say this is a line equation. If you consider the line equation here, where R is the constant proportionality value, for giving different values of R, we will get different points on it, isn't it? So if you use the actual DCs, the exact values of the direction cosines of the line, so this R is nothing but the exact distance from one point to the other point on the line. Say, you accept for that? So while taking the DCs, we are considering the projection that you say. You imagine the case of cos theta. By taking, maybe if I say like this, then again you will get confusion. So here, if you put r is equal to 1, you will get 1 point here. If you put r is equal to 2, you will get another point here. So for every r value, you are getting points on it. So while taking the DCs, r is nothing but the exact distance between the two things. 1 unit distance, 2 units distance, 3 units distance. So if you take P is the starting point, G1 is the intersecting point, PZ1 is nothing but R. You understand like that. PZ1 is nothing but the distance between 2 points, the actual value. That will be attained by taking x is equal to 0 there. Because it is meeting the planes. YZ plane, ZX plane as well as XY plane. Right. Because we have a small visualization problem for these problems. Right. So the value of R will be equal to PZ1 only when it meets the YZ plane, nothing but x equal to 0. That's why I have made it like this. Right. Now coming for the second part of the problem, you are taking the sum of the squares of the distances here. So let us consider sum of the squares of the distances. It is nothing but k square. He specified there. You have calculated the values earlier. These values, substituting it there, you got it the value as so this implies 1 by p square into now if you substitute the value of p there, you will get the required locus. Substituting p value, you have so this is the locus of the point P, alpha, beta, gamma. In other words, if we have drawn normal at a point to the conicoid such that if the normal is intersecting the three planes, then the point at which you have considered the normal, this is the locus of the point satisfied by that. That is the locus equation. Okay. Now understand one thing, that the same kind of problem will be asked on ellipsoid. So there also, if you consider ellipsoid equation and if you consider the normal equation like this, we will get the values of PZ1, PZ2 and PZ3. How we are going to do? I will just write the equation of the normal. So it is nothing but for ellipsoid, if we have considered the equation of the normal, it is x minus alpha by alpha p by a square, y minus beta by beta p by b square, z minus gamma by gamma p by c square. This is the normal equation for ellipsoid. So by substituting x equal to 0, we will get one distance which is pz1. So from this you have pz1 is equal to minus alpha by alpha p by a square. So alpha gets cancelled, nothing but minus a square by p. Similarly, we will get the other distances as minus b square by p and minus c square by p, the other distances. So we should be careful in considering the normal equation. That's it. So if we have taken the conicoid, the distances will come like this. If we have taken the ellipsoid, the distances will come like this. So from the point to the principal, you are calculating the distance. So you just imagine that if this is the plane, this is a point P. From this point, I have considered the normal. The normal intersected the plane at the point Z1. So you are calculating the value of PZ1 there, the perpendicular distance. Okay? Fine. So this is the next problem. So please read the problem and note down the problem carefully. Then I discuss with the approach. Understand one thing, that while solving these problems, the problems are interrelated. It means we are using the concept of the previous problem while solving the present problem. So we are retrieving the results what we have studied already while solving the present problem. Okay? You keep in mind the task. Now, in this problem, I have considered the ellipsoid. So before going to start the problem, as per the previous case, we have studied that if you take a point P on the ellipsoid, say this is my ellipsoid, I have taken a point P on it. At this point, I have taken a normal to the ellipsoid. This normal is intersecting the three coordinate planes at the points G1, G2 and G3. So we have the respective distances PG1, PG2 and PG3. I have already computed the values by writing normal equation that Pg1 is minus a square by p, this value minus b square by p, this value minus c square by p. Just now I have taken those values. Accepted? Understand that by default I have taken the normal equation as x minus alpha by alpha p by a square, y minus beta by beta p by b square, z minus gamma by gamma p by c square. Understand one thing, that the point P, alpha, beta, gamma is on the given ellipsoid, and at this point you are considering a normal to it. This is the equation of the normal, and these are the actual distances values if the normal meets the three coordinate planes. This is one part you have to understand and present it in the exam. So how these values came? After writing the normal equation, if you put x equal to 0, the value is equal to Pg1. So Pg1 value is minus a square by p. If you put y is equal to 0, you will get Pg2. Similarly Pg3. This part you have to write in the exam first. All of you clear? Then the second thing is, one relation is given in the problem. On this normal, I have taken one more point Q. Let us take that the coordinates of Q are nothing but x1, y1, z1. So we have to prove that the point Q satisfies this condition, the locus of Q. The solution is already given in the problem. And how the point is chosen on the normal is 3 times distance between PQ is equal to sum of the 3 distances from the principal planes. Plane 1 distance, plane 2 distance, plane 3 distance. If you sum up these 3 values, it is equal to 3 times the distance between these 2 points on the normal. In such a way, the point Q is taken. Okay? So, the point Q is on the normal. So, in the normal equation, in place of x, y, z, I am substituting the point. So, x1 minus alpha, y1 minus beta by this, z1 minus gamma by this, because the point lies on the normal. You take that this is equal to R. So if you equate the values, we will get that x1 equals to alpha plus alpha PR by a square, y1 is equal to beta plus beta PR by b square, and z1 is equal to gamma plus gamma PR by c square. These are the respective coordinates for the point Q. Okay. Since the point P lies on the ellipsoid, I want to substitute the value of p coordinates in the given ellipsoid. So what we will get? Alpha square by a square, beta square by b square, gamma square by c square is equal to 1. Because the point P is lying on the ellipsoid. Now my intention is, in order to calculate the locus, I want to find the values of alpha, beta, gamma, and I am going to substitute the values here so that I will get the respective locus. That is my whole intention here. So if you summarize the whole process, what I did, I have taken 3 points here. At the first part, I have written the normal equation. From this, I have calculated the distances. Second, I choose the point Q as per the problem description. These are the coordinates of Q. Third step, at which I am calculating the normal, the point is also on the ellipsoid. So I have substituted the point in the ellipsoid equation. In order to get the required locus, in this equation, if you observe, this is alpha by a whole square, this is beta by b whole square, this is gamma by c whole square. I want to calculate the respective values of alpha by a, beta by b and gamma by c. If I substitute those values here, I will get the respective locus here. That is my whole idea in solving the problem. Okay? Are you getting the content? Now I am going to substitute the respective values. Let us take that the distance between the 2 points PQ is equal to R. We have one equation given that in this, let us substitute the values. So 3R is equal to from this you will get the value of R as accepted. Now I have already mentioned the coordinates of Q. This is X coordinate, this is Y coordinate, this is Z coordinate. In the coordinates of Q, I am substituting the respective value of the R, the parametric coefficient value. So if I substitute that, I will get the values as x1 is equal to alpha minus alpha into a square plus b square plus c square by 3a square. That you can take it as alpha into 2a square minus b square minus c square by 3a square. So from this, you can write the value of alpha by a is equals to 3ax1 by 2a square minus b square minus c square. Please check that. Now, similarly, I will calculate the values of beta by b, gamma by c. So what I did, I calculated the value of R, substituted in the coordinates of Q. From the coordinates of Q, I am calculating alpha by A, beta by B and gamma by C values. So if you calculate beta by b value, it is 3by1 by 2b square minus c square minus a square, and gamma by c is equal to 3cz1 by 2c square minus a square minus b square. So in this main equation, I am substituting the values of alpha by a, beta by b, and gamma by c. I will get the required locus. That is the whole idea of the problem. So it is a little bit typical. So please try to understand that. In the ellipsoid equation, I have substituted alpha, beta, gamma because alpha, beta, gamma is the point lying on the ellipsoid. Accepted? Right. Now, this is nothing but alpha by a whole square plus beta by b whole square plus gamma by c whole square is equal to 1. The equation what I have written here. So for these values, I have taken the values from the point Q. This is alpha by A, this is beta by B, this is gamma by C. Accepted? So if you substitute them here, then you will get the required locus, the problem locus which is there. Alpha, beta, gamma are eliminated. And that contains only the values x1, y1, z1, nothing but the coordinates of Q, which is nothing but the locus of the Q. Clear now? So these are little bit typical to understand what is the way to solve a problem. Initially, slowly we'll understand the way. So this is another problem similar to the previous one, but somewhat easy. So first take a note of it, then we discuss the approach. Right? So let us draw a small picture for understanding. So this is the ellipsoid. This is the point P. At this point, a normal is drawn to the ellipsoid. So the point P is nothing but alpha, beta, gamma. Since the point lies on the ellipsoid, first of all, substitute the point in the ellipsoid. So if I substitute suitable values of alpha, beta, gamma, then this is my required locus of the problem. And how alpha, beta, gamma are chosen is the condition given in the problem. So if you read the problem, he has taken one more point Q. Let us say the coordinates are x1, y1, z1. And how the point is taken on the normal such that if you consider the distance PQ, the value of PQ is nothing but lambda square by P, the distance between these 2 points. Here lambda is a parameter, small p is the length of the perpendicular from origin to the plane. This is the thing given. So using this condition, if I calculate the locus of Q, I will get the solution like this. Is the idea clear? Right? So the first step, I have to write the equation of the normal. I will write the equation of the normal. So I will make space here. Equation of the normal is x minus alpha by alpha p by a square, y minus beta by beta p by b square, z minus gamma by gamma p by c square. This is the equation of the normal we will consider. So let us take that this is equal to r, the parametric value. Now every point on the normal will be of the form x is equal to alpha plus alpha rp by a square, y is equal to beta plus beta rp by b square, z is equal to gamma plus gamma rp by c square. So if I take a suitable value for r, I will get the point Q. Accepted? I need to check what is the value of r. I need to substitute there so that I will get the coordinates of Q. In the problem, it is given that the distance between PQ is nothing but lambda square by P. So in the parametric form, in place of r, I am substituting lambda square by P so that I will get the coordinates of Q. So x1 is equal to alpha plus, in place of r, I am substituting lambda square by P. So y1 is equal to beta plus, again in place of r, I am substituting lambda square by P. Similarly, z1 is equal to gamma plus, in place of r, I am substituting lambda square by P. Okay? To get the coordinates of Q, what I am doing? So if you substitute the values, exactly, please understand, capital P means the point on the ellipsoid, small p means it is the distance from origin to the center of the ellipsoid, I mean the tangent plane. If you take 0, 0, 0 is center of the ellipsoid, from ellipsoid to the tangent plane, the distance is small p. Please understand the difference. Okay? So for another visualization, you can draw that this is the ellipsoid, the center is 0, 0, 0. This is the point capital P at which normal is taken. So at this P, I have taken a plane. So from origin to this place, the distance is small p, length of the perpendicular. This is the normal actually taken. On this, I have taken a point Q. This is the whole idea. In 3D, we can visualize. In 2D, it is not possible. But the idea is like that. Small p denotes length of the perpendicular. Capital P is the point on the ellipsoid. Okay. So, while writing the parametric form, I have written small p in the normal. So, what I have written? X minus alpha by alpha p by a square. Here, p stands for the distance. So, if you take that this is equal to r, I have taken that r is equal to lambda square by p because it is given in the problem, r value. The point Q is taken in such a way that the distance PQ is equal to lambda square by P. Fine. Now it is making sense for you? All of you. Right. Now we are almost finishing the problem. So I have written the coordinates of x1, y1, z1. The coordinates of Q I have written. In place of R, I substituted the value. So we will get that x1 is equal to alpha plus alpha lambda square by a square, which gives that on taking LCM, alpha is equal to a square x1 by a square plus lambda square. Similarly, if you write the second coordinate, y1 is equal to beta plus beta lambda square by b square. If you take LCM, you will get that beta is equal to b square y1 by b square plus lambda square. Similarly, I will get the third coordinate z1. So I got the three values, what is alpha, what is beta, and what is gamma. So I substitute the values here, alpha value, beta value, gamma value. This is my required locus, what I will get. If I substitute alpha, beta, gamma values in this equation, I will get this locus. Please check that. All right. So there is one more problem here we have to discuss. Since we are the shortage of time, I will give the posters for you. You can read that. Because we have majority of the problems to discuss. So many problems are there. But I will give the posters for you. Because on reading the question part, you will understand. So at this part, I want to mention one thing. So what is lambda here? A parameter, right? If you consider LCM for this expression, what could be the degree of lambda there? Are you finished with this problem? Please tell. Right, that is 8. That is correct. Now I want to discuss something interesting for you. If I rewrite the whole thing, you will get understandable. So just I want to take that consider thing, x square by a square plus y square by b square plus z square by c square equal to 1. This is the equation of the ellipsoid. So for this ellipsoid, I have taken an external point x1, y1, z1, let us say. So if you take a point P, alpha, beta, gamma on the ellipsoid. Let us write the normals for it. So here I am not measuring any distance. So I will write the normal equation as this is the equation of the normal to the ellipsoid at the point P. Suppose this normal passes through the given point x1, y1, z1. So substituting here, you will get x1 minus alpha by a square, y1 minus beta by b square, z1 minus gamma by c square. You take that the parameter is lambda. At a value of lambda it is taken. So if you simplify this, we will get that x1 is equal to alpha plus lambda alpha by a square, y1 is equal to beta plus lambda beta by b square, z1 is equal to gamma plus gamma lambda by c square. Now, if you simplify this value, we will get that alpha by a is equal to ax1 by a square plus lambda. Beta by b is equal to by1 by b square plus lambda. Gamma by c is equal to cz1 by c square plus lambda. So just understand, I have written the normal equation at a point P to the ellipsoid. The normal passes through the another point. So I have substituted the point in the normal equation where the parameter value is lambda. I have considered the respective coordinates. From this, I have taken the values of alpha by a, beta by b and gamma by c. Since the point alpha, beta, gamma lies on the ellipsoid, I can write that alpha square by a square plus beta square by b square plus gamma square by c square is equal to 1. So it is nothing but alpha by a whole square plus beta by b whole square plus gamma by c whole square is equal to 1. If I substitute these values in this part, I will get the locus as this is the locus I will get. Please check. This is very close to the problem what I solved just now. There one condition is given. Here we are not taking any condition. I have written the normal equation. I have taken one more point on the normal. I have written its coordinates. So what is the locus satisfied by that point? So this is the locus satisfied by that point that I have written. Now if you observe, by taking LCM for the denominator, you can observe that the equation will have degree 6 in lambda. Accepted? A square will be cancelled there. B square and C square. Actually, alpha by a whole square means this total value whole square, isn't it? Yeah. So you are saying that x1 square by a square plus lambda whole square, y1 square by b square plus lambda whole square, and z1 square by c square plus lambda whole square is equal to 1. That is what we're saying, right? Because a square gets cancelled, right? Let us remove that. You agree with this, locus? Just understand, I have taken the value of alpha by a here. Alpha by a is nothing but this entire value. Will you agree? That's why the values will remain as it is. Is my point clear now? Thank you. So if you have taken alpha value exclusively, you are correct. In denominator you have something, a square gets cancelled. But I have calculated alpha by a, not alpha. There is a difference. Thank you. Now my intention here is, if you take LCM, it is an expression having degree 6 in lambda. Agreed? So what happens here, lambda is a parameter. Since it is 6th degree equation in lambda, if you calculate the roots, you will get 6 values for lambda. Accepted? So by substituting different values of lambda there, you will get different points. So you will get exactly 6 points for this locus. It means that from an external point x1, y1, z1, we can draw normals to the ellipsoid. At the normals will meet the ellipsoid at 6 different positions. The intention, what I am going to say is, the number of normals can be drawn from an external point to the ellipsoid is 6. We can draw 6 normals to the ellipsoid from a fixed point. You can imagine the case that from this point, this is one normal, this is one normal, this is one normal, like that. So total you will get 6 points on the ellipsoid. These are normals taken from a fixed point. Okay? I am leaving the visualization part for your sake. Please understand. You just understand the content. All of it clear? So I am going to say one more thing. So this is the ellipsoid. Degree 6 I am saying. So if you simplify this expression, take LCM. What is the degree of lambda there? Is it 6 or not? 4. I have 3 things. Lambda, 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 3 things are there. On the product I will get lambda power 6. If you take LCM, I will say that a square plus lambda whole square into b square plus lambda whole square into c square plus lambda whole square. Then if you consider the product, we will get lambda power 6 or not? In denominator it will become 6. Say. So right side you have 1. If you take denominator to the right hand side, you will get 6, right, for lambda. That's what I am saying. So for position of degree 8, it means that you have taken a measurement PQ, right? So if you choose a point Q, From that point, you can draw normals to the ellipsoid at 8 different positions on it. That you can visualize. We can call like that. So for a good visualization part, I can say that suppose the point Q, what you have taken is a satellite, let me say. This is the ellipsoid you have taken. So the normals are nothing but you can access directly at 8 positions or 6 positions. Direct communication you have, that you can understand. For an idea, you can imagine like that. The normals in other sense. That's it. So my intention here is from an external point, if you draw normals to the ellipsoid, the normals you can draw at 6 different places. 1, 2, 3, 4, 5, say 6. Now understand that these 6 points will lie on a curve. And this curve has degree 3. So it is a cubic curve. And how I am getting a curve? As we know, if a sphere is intersected by a plane, you get circle. If a cone intersected by a plane, you will get a curve. Similarly, if an ellipsoid intersected by a plane, you will get a curve. So on this ellipsoid, I am calculating a plane such that on the plane, these 6 points will lie. So I will give the postures for you. You can read that and you can understand that. So on this plane, these 6 points will lie. So you will get a curve of intersection and it is a cubic curve. Okay. And one more thing is, basing this curve as a base curve, this is a vertex, you can generate a cone. So this is the external point. I have taken normals. It will meet at 6 different places. These are nothing but formed by a curve. So it will generate a cone for us. This is the overall idea. Okay. I will give the respective postures for you in Telegram. You read that, you will get the whole idea, what it is actually. The solution is very clear. Just write in the generator equation, you will get the solution part. Nothing difficulty is there. But the whole idea about the normals is, if I want to summarize the whole thing of today's session, first point is, if you take a point on the ellipsoid, you can draw the normal on it. If the normal meets the principal planes, what it happens, how to calculate the locus. That is one concept we have discussed today. Second, from an external point, if you try to draw normals to the ellipsoid, you can draw normals to the ellipsoid at 6 different places. The next one is the feet of the normals at which the normal meet the ellipsoid. The feet of the normals, the 6 points, will be on a curve. It is a cubic curve. And basing that as a guiding curve, you can generate a cone. There is a specific equation for it, I will give you. And how the curve is formed, if you calculate a plane passing through the 6 feet of the normals, you will get the curve. That is the whole idea. Clear? So I will give the postages, you can check. And we have one more concept in the chapter, that conjugate symmetry diameters. So in tomorrow's class, I want to take some of the problems on it. On the whole, if you summarize the conicoid chapter, we have done some problems on ellipsoid, some problems on conicoid. Now we have done some problems on normal. Tomorrow we are going to do the concept of semi-diameter. Please understand that we didn't do any problem on paraboloid and hyperboloid. Actually, problems were not asked in on these concepts. I will give the postage of some problems with regard to paraboloid, because the concept of ellipsoid, how to calculate the tangent plane, how to calculate the plane of contact, if you know them, it is very easy. Same formulas we are repeating again there. So I will give the respective postages for the problems with regard to paraboloid. And generally questions on hyperboloid are not at all asked. So this is the whole idea with regard to conicoid preparation. Please understand that there is no need to read the questions separately and exclusively on conicoid chapter. Majority of them are repetitions. So as per the weightage is concerned, don't pay much attention to this chapter, right? Because there are other chapters to concentrate and which are very easy to solve to get a good scoring. That is my suggestion for you. So it is up to yours to prepare in detail with regard to conicoid or not. As per your interest, you can do. Because much time you have to dedicate on the preparation of conicoid. If you have taken concentration for paraboloid and hyperboloid also, you can understand that class questions are sufficient. That is what I am saying. I have taken majority of the questions which are nothing but the previous year question paper questions, and I will give the supplementary material for you. I will give in Telegram the random postage of questions. You can read at your convenient time and you can prepare them. That is enough. No separate preparation or material is required if we have good understanding with regard to conicoid chapter. That I give one suggestion for you. So let us wind up our session here. Tomorrow we will meet with the last concept, conjugate semi-diameters. Thank you. I can say that this session will be somewhat difficult for you compared to the previous classes, the today's session, because it involves the visualization part more to get the idea. I hope. So thank you very much. We will meet tomorrow.